Alright, so welcome back to the last segment of the final module in week 4. If you remember, we have been discussing the problem war. So I should point out that this video is the last in a series of 3 videos, and in the first one we introduced the problem statement, and in the second one we described a solution. And in this short wrap-up video I'm going to show you some snippets from an implementation of the solution that we discussed in the previous video. So I would not expect this to make any sense if you haven't seen the previous 2 videos, so please make sure that you've watched those first. Our implementation is going to be in C++ because we'll want to just build on the union find class that we described in the first module, but it should be pretty straightforward to translate this into your favorite programming language. So if you do end up doing that, please do submit a pull request to the official repository. As always, we'll look forward to receiving your submissions. So with that said, let's proceed to the implementation. So I'm just going to begin by looking at what the union find class looks like. We've just essentially introduced a public entity called enemies. This is to keep track of the enemy pointers on the leader elements, and the rank and friends are the usual things from the default DSU data structure. So friends is just a renaming of the parent array. I think we've been using P to denote the parent pointers previously. Now I've just renamed that to friends, just to remember that we're keeping track of the friendship relationship using these pointers. So the initialization is pretty straightforward. For friends and rank, it's as before. In fact, in the problem statement as well, you'll see that it's been made explicit that everybody is a friend of themselves and nobody is their own enemy. So the friends are singleton sets to begin with, so that's our standard initialization. And for enemies, we just want to basically say that we're starting off with a blank slate and there are no recorded rivalries right in the beginning. So we just follow the convention that we're going to use a value of -1 to designate that this person has no known enemies at the moment. So that's a simple initialization. And in this problem, the n people are in fact indexed from 0 to n-1. So in the previous module, I've been saying that I'd like to initialize union find with n+1 because, for example, in destroying array, the elements were indexed from 1 to n. But here you can just do a standard instantiation with just n, and your indices will work out fine. It's quite peaceful actually. So let me just begin by also introducing these 2 new methods in this class. So we have our friends and our enemies. You'll notice that our friends behaves very much like is same set. You just check if the leaders are the same and you return an appropriate value. As for as enemies, here what we want to do is check if the leaders are enemies of each other, and if that happens to be the case, then we return yes, and otherwise we return no. So this is exactly as we discussed, and these are 2 really simple helper functions to write and get out of the way. The crux of the matter is really in figuring out the make friends operation. So again, I'm not showing you the parts of the code where we take in the input and do the case analysis and all that. That's fairly straightforward, and in any case you can always look up the full code from the repository. So I'm just going to show you some relevant snippets corresponding to the cases that we discussed. And even here for make friends, I've not shown you, at least not on the screen right now, the case where we handle the contradiction. So the very first thing to do is check if the input to make friends, which in this case is x and y, you want to check if they are enemies, and if that actually returns yes, then you want to output -1 and just break out of this case altogether. So that's a sanity check that you do need to do up front. And once you're out of that situation, essentially you replace the people x and y with the corresponding leader elements. And the first case, which was the simplest one, was a situation where x and y have no known enemies to speak of. So if the enemy array is -1 at both these indices, then we just do a simple union and that takes care of the situation completely. But now we have a situation where one of the leaders has an enemy and the other one doesn't. In this case, remember what we said is that you can infer a new enmity, right? So X and Y are about to become friends, and let's say X has a known enemy, then that known enemy also becomes an enemy of Y. But the way that this plays out in the data structure, the way we are maintaining things, is that you go ahead and you do the merger between the clusters of X and Y. And what happens now is that it's possible that Y may have taken over as the leader, in which case you need to make sure that the enemies array is appropriately updated. So that's exactly what is happening here. First, you identify the enemy of X, then you merge the sets that X and Y are currently representing. And now, just for the record, you look up the representative of this merged set and you make sure that this representative becomes enemies with Z. It's possible that nothing changes in the enemies array because possibly X is also the new representative, but just in case Y has taken over, this ensures that the enemies array is properly updated. Now I'm going to skip case 2b, which is the exact symmetric situation where Y has an enemy but X doesn't. It's essentially the same logic, but with, of course, the variables appropriately swapped. The final case was when X and Y both have enemies. Remember that in this case we said that the sets that contain these two enemies can also be merged because these two enemies can now be inferred to be friends between them. So let's say that A is the enemy of X and B is the enemy of Y. So we merge X and Y because that's what we had set out to do anyway. But by inference, we also merge the sets that are being represented by A and B. Now what we have to do is once again make sure that our enemy pointers are appropriately updated. So we have these two merged clusters. We identify the potentially new leaders of these clusters, and then we make sure that we put their enmity on the record. So that takes care of all the scenarios that could arise with make friends, and it's similar with make enemies, although the details are slightly different. So I think the most non-trivial case for make enemies was again the case when both of the people who are involved, both of the leaders, have enemies of their own. So let me just show you that one case, and remember that this is, unlike in many of the other videos, this is not a line-by-line breakdown of the entire code. I'm just showing you the parts that I think are the most interesting and non-trivial, and I hope that what you will be able to do from here is to actually write out all the cases by yourself. And of course, if you do need to look at the entire code, you could always take a look at the repository, which is linked to in the description of this video as well. So let's wrap this up with a look at the last case for the make enemies operation, which I think is the one where there's the most going on. So let's say that you're supposed to be making enemies of X and Y, and let's say that they have enemies of their own which are denoted by A and B respectively. So let's say X has a known enemy in A and Y has a known enemy in B. If you go back and think about how we dealt with this case previously, we said that well, when that happens, so X and Y are the two people on the top and A and B are the two people on the bottom, then we said that, well, we need to make friends between let's say X and B and Y and A, because those are the additional friendships that we were able to infer by the common enemy rule. So that's exactly what we do in the code. So we say that well, if A was an enemy of X, then A and Y have a common enemy in X after you establish the enmity between X and Y, which is what you've set out to do. So because A and Y have a common enemy in X, we are going to go ahead and merge the sets that A and Y belong to, and for a very similar reason, we are going to merge the sets that B and X belong to. So after these mergers have been established, we still need to make sure that these big merged sets are actually enemies with each other as well. So let's make sure that we pull out the leaders of these newly created sets and establish the enmity between them. So that's exactly what is happening in the last 4 lines of this code snippet. So of course you do have a few other cases to deal with for the make enemies relationship as well, when you have one of the leaders having an enemy and the other one not having an enemy, and the even easier case is when neither of them have a known enemy, in which case it's just 2 lines to update the respective enemy pointers. And even before that, don't forget to check for a contradiction before you get into any of these cases at all. If X and Y are already friends, then you just output -1 and break out of this case. So again, there needs to be a little bit of a wrapper to make sure that you get into the right cases in the right situations based on what the input looks like. So you can go and look at the problem statement to make sure that you have the right formatting in terms of input and output. But at this point, I think you hopefully have enough information to piece together your own version of this solution. As I've said before, this is by no means the only approach to this problem, but I found this way of solving it to be fairly natural and actually quite elegant, really, once you have an understanding of all the possible scenarios that emerge. So I do hope that you enjoyed this as much as I did. I will say that this is probably one of the more challenging problems that we have seen so far in this course. So if it takes you a while to sort of really absorb all the cases and what's going on, then do take your time. I think this problem does require a little bit of patience, but I think it's well worth it at the end. So do let us know how it goes. Please drop in a comment if you have any questions or any suggestions, and we'll look forward to hearing from you. And with that, it's a wrap for week 4. So I hope you enjoyed this little excursion through all the ways in which disjoint sets turn out to be useful. And as I said, we'll probably keep encountering this data structure. It's something that also shows up, as I've mentioned earlier, in more advanced problems as something that's a piece of a bigger puzzle. So I think this little bit of practice really is going to be handy. And fortunately, there are a lot of really great resources for learning more about disjoint set union or union find or disjoint sets or whatever you want to call it. If you're interested in the theoretical aspects, you will find a link to a really wonderful book chapter in the description of the first module or on the course website. That's a great resource for learning more about why path compression works out so well and so on. And if you just want to try more practice problems, then the Code Forces education segment on disjoint set union is a great place to start. They have tons of problems in increasing order of difficulty, roughly speaking, and they also have some great video materials. So if you really want to dig deeper, there are a bunch of resources, and we'll link to some of them in the description of this video. So I really hope that you have fun exploring, and I hope that you do actually get to use this in a contest that you participate in the future. So as always, have fun, and please keep the conversation going on Discord and on the mailing list, and I will see you back next week.